In our earlier lectures discussed in the month of September, we have discussed the definition of homomorphism. In this lecture, we want to start the isomorphism, which is in our fifth unit. But before discussing on the isomorphism, it will be better to recall the definition of homomorphism. So let us recall the definition. Let us suppose we have two groups G and H. I am giving the name G and the name H. The group G having some elements and similarly group H having some elements. If the elements of group G are associated with the elements of group H, then this association or this relation is called a mapping. So it means the group can have some different type of relations or mappings. So in this case we are going to discuss on some specific relations between groups. The first is homomorphism. So let us, there is a group Z having an algebraic structure and the composition is star. This is the binary composition, and you can take any meaning of this star or as per the defined in your problem. And there is one more group which is H, and here dot is the composition. So there is a relation between G and H, and this relation is denoted by Q. Then this relation or mapping is called, here we are not giving the name relation because you can find the different meaning of relation from discrete mathematics, as I have discussed earlier also. Here we will call it as a mapping. Mapping means correlation or association with the elements of G with elements of H. So here I am calling it as mapping. So there is a mapping between G and H. Then this mapping is called homomorphism if the composition of two elements available in group Z and the output and get the output. Let us suppose the X and Y, this is the first element and first element is X and this is the second element which is Y. As G is a group, so the closure property will hold. It means the composition of these two elements will be available in G. Let us suppose that is Z. Then what will be the mapping of this element Z? The mapping of this element Z or the association of this element Z will be another element available in H, and that is the composition of their individual mappings. It means if X is mapped on phi of X, Y is mapped on this element phi of Y, then their mapping of their composition will be equal to the composition of their mappings. Let us suppose the mappings of the first element is X dash and the mapping of the second element is Y dash. Then the composition, which is the operator, this is the operator which can be defined in different problems differently, but here you can treat it at a dot. So if you could find the output of these two elements, let us suppose this is Z dash, then this Z will be mapped to another element, that is Z dash. So simply we can define as the mapping of the composition of two elements will be equal to the composition of their mappings. So this will be called homomorphism. For an example, let us suppose we have a group and algebraic structure R plus, it means the set of real numbers with addition, and there is one more set of real numbers with multiplication. Let us suppose this R contains the elements of the type of e to the power x. It means it will contain the exponential functions over the real numbers. So let us suppose e square is the first element of this set and e to the power 4. This is the second element of this element. So what will happen here? The mapping of their composition. It means if you could add e2 plus e to the power 4, e2 and here the composition of x plus y, not element. These are this is x and this is y. The composition of 2 plus 4. If you could map, the mapping of this element will be equal to the map composition of their individual mappings. It means that will be equal to e to the power x and e to the power y. because this is the relation phi. This is a relation phi in which the mapping of element x can be expressed by e raised to the power x. Similarly, the mapping of another element y can be expressed with the element e raised to the power y. So the mapping of their product must be represented as the mapping as the exponential of their addition. This is as per the definition of homomorphism. Now, if you apply solve it mathematically, then it can be broken as the product of the two different elements e raised to the power x and e raised to the power y. And in this case, the first element is the mapping of x, while the second element is the mapping of y. So here, the mapping of the composition of two elements is equivalent to the composition of their mappings. So here, this phi is called homomorphism. If a mapping is homomorphism, then it can be monomorphism. It is the special type of homomorphism. If phi is a mapping which is homomorphism and it is mandatory, phi is 1, 1. Then in this case, this homomorphism is called or can be expressed by another word, monomorphism. For an example, let us suppose we have this type of association, and here we are looking that one element is associated with one element only. So this mapping is called 1, 1, and in this scenario, this mapping is called monomorphism. The another definition of is apomorphism. In the case of apomorphism, phi must be a homomorphism. It means it will satisfy the previous definition, as well as it is own to. Own to means there will be no element in the second group which is not mapped on any element of the first group or by the any element of first group. Here you are looking that this is the middle element, this is not the mapping of any element from G. Let us suppose this is G and this is H. Here we are seeing that there is one element available in H which is not the mapping of any element of G. So it is in two case. This is in two case. But in onto case, every element of this set or group H must be mapped by any element of group G. For an example, there are 4 elements in first group G and 3 elements in group H. The first 2 elements are being mapped on a single element, but in H there is no such element which is not the mapping of any element of G. So this is the onto case. So if this mapping is onto, then it is called apomorphism. This mapping can be naming as isomorphism. It means we can give one another name, isomorphism. If this mapping is 1, 1 and onto, it means there is no such element in H which is not the mapping of any element of G, and every element of G must be mapped on a single element on H. Let us suppose this is mapped on this element and this is mapped on this element and this is mapped on this element. Here we are seeing that the one element is mapped on 1. It means no more than two or more than 2 elements are being mapped on a single element on G, on H, and there is no element in H such a way that which is not the mapping of any element of G. So it is 1, 1 and onto case, and in this scenario, this mapping homomorphism is called isomorphism. Some objective type question can be asked in your exam from this portion. And the last is endomorphism. In the endomorphism, the element of a group G must be mapped on the element of group G. It means the element of a group will be mapped inside that group. So let us suppose these are 2 elements X and Y, and here there are 2 elements X and Y, and here I am saying that this X is being mapped on Y and Y is being mapped on X. So this is called endomorphism. So today you will learn and write the definition of homomorphism, isomorphism, endomorphism, etc. And during the next lecture we will discuss some examples and theorems based on the isomorphism. Thank you so much.